Welcome to Geography 105, Weather, Climate, and You Online. This is Unit 2, Earth-Sun Relationships. To start the lecture for today, I'd like to just focus a second here on this rather simple question, but it can be quite confusing depending on who you ask. What causes the seasons? You know, not everywhere across the Earth receives 4 seasons like we do here in Chicago: spring, summer, fall, and winter. So a simple kind of question to pose would be, what is the reason that we have seasons? And it's interesting, this question was posted to a class of Harvard graduating students, and only about 65% of those students got this question correct. And so some of the more common answers were sunspot solar activity causing seasons. One being the distance from the sun, which would make sense because actually at different times of the year we are at different distances from the sun. So you would think when we're closer to the sun we'd have warmer temperatures, and when we're further away from the sun we'd have cooler temperatures. But actually both of those are incorrect. The reason that we have seasons in the mid-latitudes of the United States and across the globe is due to the tilt of the Earth on its axis. The Earth is actually tilted 23.5 degrees from true north vertical, and I'll show you an image of that here in just a second. And it is the reason that we have seasons here in the mid-latitudes. So when we are tilted toward the sun, we receive the northern hemisphere summer. When we are tilted away from the sun, we receive the northern hemisphere relative winter time. And it's vice versa in the opposite of the hemispheres. So while the northern hemisphere is experiencing summer, the southern hemisphere is experiencing winter. I've got a couple graphics that'll help show you this in just a second. So we're going to talk about some of these Earth-Sun relationships, how they govern incoming solar energy, temperature patterns, the amount of radiation that's received at the surface, and then the amount of daylight length. To understand this, you should have a pretty good handle on latitude and longitude by now. Just very quickly, some of these things here that I have on the slides that are in bold, these would be gaps in my normal lecture. So if you were sitting in this lecture on campus at COD, you'd be filling in the orange colored words in sort of like a Swiss cheese version of the notes. So you'd have to come and fill in the notes in order to get this. So when you see those bold, those are typically the more important things. Those are things that I think the students should be writing down as we go through. Obviously, you have a digital copy of these notes in slideshow format, so it's not going to be a big deal for you. Don't forget, longitude starts measuring at the prime meridian. We count number of degrees, so 360 degrees all the way around the sphere. You can go 180 degrees east or 180 degrees west. That would meet at the international date line, which is opposite of the prime meridian. So sometimes you'll hear me call these meridians throughout lecture. Meridians are just referring to lines of longitude. They run north-south and converge on a point in the northern and southern hemisphere, which is the north and the south pole, respectively. Throwing the lines of latitude, or sometimes referred to as parallels, we have 90 degrees of those, so 90 degrees north of the equator, 90 degrees south. You can be anywhere 0 to 90 north or 0 to 90 south. If you leave out the north-south, you can most people just use positive or negative signs to indicate what hemisphere that these are in. If you look at the radius of the circles of latitude across the globe, and I'll try to illustrate this with my mouse cursor, as we get closer and closer and closer to the North Pole, essentially the radius of the circle is getting smaller and smaller until you converge on the point at the North Pole. So if you can imagine the Earth as an apple and you're taking slices through the apple, that radius would get smaller and smaller until you converge on that tiny point, which would be, in this particular picture, the North Pole. Slap latitude and longitude together and you get the latitude-longitude grid. It's fairly straightforward. In the case of latitude is that we're equally spaced, and longitude is actually not. So when you go north or south of the equator, latitude will always measure a constant distance, meaning 1 degree of latitude is the same no matter where you're at. That's not the case for longitude. As you'll notice, the distance between meridians down at the equator is much greater than the distance between meridians towards the North Pole. So there's an equation that you can use to figure out the distance between 1 degree of longitude given what latitude that you're at. We're not going to focus in on that in this particular course. We're interested in understanding the latitude-longitude grid. If you throw in elevation, which would give you the vertical sort of axis, then you could pinpoint a three-dimensional point on the surface of the Earth or even into the atmosphere. So if I gave you a latitude and a longitude and an elevation, you could arrive at some space or some point in a three-dimensional space that would get you to the described location. At the bottom here I have a question. What are Glen Ellen's coordinates? Glen Ellen, the location of campus. And yes, we are north of, hopefully you know we're north of the equator. We are west of the prime meridian, so we would be measuring either in negative degrees longitude or degrees west. And it just so happens that Glen Ellen is about 42 degrees north, 88 degrees west. So if you're measuring, we are about smack dab in what I call the mid-latitudes. If we have 0 to 90 north latitude, halfway would be 45. So 42 is sitting right in about the middle portion of the northern hemisphere. And 88 degrees west, you would measure 88 degrees west from the prime meridian. That's going to put you right in the western suburbs. Taking different views of the geographic grid to start understanding where we're located relative to other features on the Earth, the intersection of 0 north and 0 east, and in fact at 0, 0 you don't even have to worry about using north or east. 0, 0 by definition would be the intersection of the prime meridian and the equator, which is going to put you just off the coast of Africa in the Atlantic Ocean at this point right here. If you look at 0 north, 180 east, the intersection of the equator and the international date line, this is where, for purposes of timekeeping, our day switches. So as essentially the first locations on the Earth to experience the next day are right here at the international date line. And at 90 degrees south, we don't need a latitude, or we don't need a longitude, because by definition, if you're at 90 south or 90 north, you are at a point. In this case, we're at the South Pole, centered over Antarctica. Hopefully you have an idea of the solar system as well too. We are, again, the third rock from the sun here, Earth. And what I said in the very first lecture was a nice cozy combination of temperature and pressure in terms of distance from our star, which I'll talk about here in just a second. Most of the stuff that we will talk about in this particular class will be the atmosphere of Earth, although we will briefly discuss the atmosphere of Jupiter and the atmosphere of Venus and some kind of characteristics of the atmosphere on Venus that are we starting to see on Earth as well. Otherwise, in terms of the other gas giants, they all do have atmospheres as well. We won't really be talking about them though. Our sun, which is the most important driver of weather and climate here on Earth, is a fairly average star. So if you take a look at all the stars across our particular, if you want to go with the galaxy and then even go to the universe or multi-parallel universe, whatever you want to talk about here, this is a fairly average star. In terms of the Milky Way galaxy, we're talking one average star of about 100 billion. The sun rotates every 35 Earth days, and another interesting thing here is that it comprises about 99.8% of the mass of the solar system, and the other 0.2% is about Jupiter, and then you start breaking up some very small fractions, 0.001 for the Earth and some of the other inner planets. So the sun is a fairly massive entity, but it's in terms of other stars in our galaxy, it's actually fairly average. The sun creates energy that is received at the surface of the Earth as a process known as nuclear fusion. This is fusion of hydrogen atoms in the core of the sun. This is different than what they're doing out at Byron at the nuclear power plant or down in Marseilles or Seneca. That is nuclear fission. This is fusion. It's a totally different process, but similar. Basically, the core of the sun is so hot that it melts down the hydrogen atoms and causes a release of energy in the radiomagnetic, or some people call it the electromagnetic spectrum, and we receive energy at the surface of the Earth through this. And we'll talk about that process in temperature and radiation lecture. However, the most important thing here is the amount of energy that is received at the Earth's surface. So depending on the orientation of the sun to the surface of the Earth, It will basically govern how much energy you get at the surface. And this is what we're going to talk about the rest of today, these ideas of these Earth-Sun relationships and this geometry that kind of sets up to govern how much radiation is received at the surface of the Earth. Okay. Here is Earth from space. We're going to be seeing a lot of images like this, especially when we start looking at clouds and weather patterns. But just a couple facts here about the Earth. The equatorial radius is 6,378 kilometers, and whereas the polar radius is about 6,356. You might be wondering how we can measure these so well. We actually can very accurately measure these dimensions now with satellites. Before it was a little more imprecise. Now with satellites we can get basically significant digits down to the tenth of a meter. One thing you'll notice about those numbers is that the Earth is a little bit thicker or fatter at the equator with a radius of 6,378. So it's almost like at the center of the equatorial regions, the Earth is a little bit bulged out. It's a little bit fatter, and the reason for this is because of the rotation of the Earth. If you can imagine the Earth spinning like a top, just like you kicking a kickball and you kicked it off center, the Earth or the object would spin out a little bit and be a little bit faster in the equatorial region. So due to the orientation of the Earth and its rotation on its axis, it's actually an oblate spheroid, not a perfect sphere, because of this oblong nature at the equatorial regions. So the three most important things, and the things you're going to actually be tested over on your first test for this particular online class, is one of the questions is going to focus on the three major properties of the Earth that have an important impact on weather and climate. So this would be one of those things you want to pull out a piece of paper or notepad or whatever and start to jot down some of these very important ideas. We're going to talk about all three of these today in depth: rotation, revolution around the sun, and also the axial tilt of the Earth. These three properties govern weather and climate on the surface of the Earth. So if you want to know the diurnal rhythms, where you're going to get X amount of radiation, where you're going to have certain temperatures, how long the days are, all of those things are governed by these three factors. First is rotation. Because the Earth rotates on its axis, so a view from space would be showing the Earth rotating from left to right, causing diurnal rhythms in temperature, humidity, cultural activities, even animal behavior. Some animals are nocturnal. They only come out at night. Cultural activities. Most people go to work during the day, come home and sleep at night. Diurnal rhythms of temperature. Warm during the afternoon, cooler in the morning. Humidity. Light. Okay. Because of this rotational component, we see these diurnal daily rhythms in our day-to-day life. The Earth's rotation also influences wind, ocean currents, and some really other cool things that we're going to talk about. This is known as the Coriolis force, or the Coriolis effect. Because you're on a rotating body, objects that travel in a free-moving environment actually are deflected one way or the other. So you could imagine taking off in an airplane from Chicago to St. Louis. You could not fly in a straight line because the Earth would be rotating underneath you. So there'd have to be some sort of correction in your bearing of your flight path in order to hit St. Louis. You're almost like leading a receiver in football. As the receiver moves from left to right, you want to throw the ball where the receiver is going to be, not where the receiver is currently at. So we're going to talk more about this Coriolis force when we talk about forces in wind, but the winds and the ocean currents, are, in terms of the direction, are impacted by the Earth's rotation. Revolution is a little bit different. This is the idea that not only is the Earth rotating, it's also revolving around the object. Yes, the sun is the center of our solar system, and the Earth revolves around that object. If you were looking down from a bird's eye view, if you could figure out what was up and what was down, the Earth would be rotating in a counterclockwise fashion around the center of the sun. And our orbit is not like this animation describes. It's much more of an ellipse, not a circle. I know this image kind of shows it as a circle, but it's much more of an ellipse. This revolution around the sun is complete. I make one revolution, so one completion every 365, what we would call Earth days, 365 and a quarter to be exact. Every 4 years, we complete the fraction 4 out of 4, and we add a day at the end of February, and that's known as a leap year. So every 4 years, when we create that 4 out of 4 fraction there, we add a day in February. The actual revolution plane looks a little bit more like this, the sun being, again, the center of the solar system. And if you were to draw this out or sketch this out, you can imagine in 3 dimensions what this would look like. We're actually closer to the sun in January than we are in July. Okay? Now, I say closer, but it's a relative closer. 147 million kilometers versus 152 million kilometers. That's about 3% closer in January than July. Okay? So we come up with these definitions, the perihelion and the aphelion. This is basically, we use these terms for comets and other planets as well, but it's basically the closest and the furthest approach away from the sun. The closest approach being the perihelion on January 3rd, and the furthest approach away of the Earth to the sun on July 3rd during the aphelion. Okay? Because of that elliptical structure, there will always be a perihelion and an aphelion in every object's orbit. So just keep in mind that, yes, even though we are closer to the sun in January, we, in the northern hemisphere here at least, are experiencing our winter season. And on July, when we are actually, the northern hemisphere is being faced away from the sun, being toward the sun, we're actually a little bit further away from the center of the Earth's in terms of distance. So the distance here, don't let that kind of confuse you. Even though we are further away in July, we are still experiencing northern hemisphere summer. And in January, even though we're a little bit closer to the sun, the northern hemisphere is being pointed away and we are experiencing our winter season. So here are these 2 terms that are going to be important for test 1, the perihelion and the aphelion. Perihelion is an easy one to remember. The prefix peri, peri, in Latin means to be near or to be close to. So you can kind of use that to your advantage there. PERMI is the nearest approach to the sun. That happens on or about January 3rd, and we call that the perihelion. So the closest approach that the Earth will make to the sun happens on January 3rd. That is the perihelion. The furthest approach away happens on or around July 3rd, July 4th. That is known as the aphelion. Okay, so even though we are further away from the sun in July, we are still in the northern hemisphere experiencing our summertime. So that's what that third kind of bullet point in that question relates to. Why would being farther away from the sun result in being hotter? Because of the Earth's axial tilt, which is the next kind of element here that we're going to talk about. If you were to draw a straight line vertical through the Earth, you would see that the North and South Pole are actually tilted 23.5 degrees off of true vertical. So, using the geometry diagram in the upper right, the North Pole creates an angle between true vertical north and the North Pole, which would be about 23.5 degrees, leaving 66.5 degrees from the North Pole to the elliptical plane. So take a look at the bullet point over on the left-hand side. This tilt causes the Earth's axis to always be pointed towards Polaris, which is the North Star. During old navigational sailing trips across the Atlantic and Pacific, sailors used to use Polaris to figure out their latitude. It's very simple to know where Polaris should be in the North sky. You knew that Polaris was directly underneath the North Pole. You could do some geometry and figure out exactly what your latitude was. Longitude was a little bit more difficult because you had to be able to keep time. In order to figure out your longitude, you have to know the time, and most clocks at that time were pendulum swinging clocks, and you can imagine that a pendulum swinging clock inside of a boat is not going to be very accurate. So they were very good at keeping latitude, not so good at keeping longitude. So, this idea of the North Pole always being pointed at Polaris, you can see what's happening here in this animation in the lower right-hand portion of your screen. Not only is the Earth rotating on its axis, it's also revolving around the sun, and so at certain points of the orbit, the North Pole is pointed toward the sun, and over here on the left-hand side, you can see the North Pole being pointed away from the sun. That's actually happening during the perihelion, during our closest approach. So it's kind of interesting to see that, yes, the perihelion would be over here, the aphelion would be over here. This is a pretty good animation or description of what this really kind of sort of looks like. The Earth is actually not at the very center of our ellipse. It's actually off-centered just a hair, and that's what creates the aphelion and the perihelion. This tilt, however, is what causes the seasons. So certain times of the year we're tilted toward the Earth, toward the sun. At certain times of the year, the northern hemisphere is tilted away. And you can see on those opposite sides, right, as the northern hemisphere is tilted away, the southern hemisphere is actually tilted toward the sun. So in the northern hemisphere, when we have winter, the southern hemisphere is experiencing their summer. So if it's not clear just yet, this slide should answer why the axial tilt causes seasons depending on your latitude on Earth's surface. Throughout the year, it affects the angle at which the sunlight strikes the Earth. It affects the amount of the atmosphere that the sunlight must pass through and the amount of daylight hours. Okay, so all three of those factors kind of culminate together to determine how much energy the Earth receives. So we have this really cool axial tilt. Yes, as the Earth revolves and rotates around the sun, it's being pointed either towards or away. But how does that being pointed towards or away actually influence the amount of sunlight and daylight length? And the answer is these three bullet points right here: solar angle, solar amount of atmosphere that the sunlight must pass through is something we're going to be called beam depletion here in just a second, and also the amount of daylight hours. Okay, let's take a look at this first one. This first idea is known as beam spreading. The image over on the right kind of shows what beam spreading looks like. Okay, they always tell you that if you go to near the equator during the summertime, be careful, you will burn. Right? Your skin will burn very easily in the middle of the day because the sun is very high above you. Right? If you go outside and you were looking to get a suntan, you're going to go out during the afternoon when you have a relatively high solar angle. So the image over on the right describes solar angle. If the sun was at the horizon, it would be a solar angle of 0. If the sun was directly over your head, you'd have a solar angle of 90 degrees. The higher the solar angle, the more intense the radiation at the surface. So, as the sun gets higher in the sky around noon, why is it most intense? Because the solar rays are focused in a very small area, whereas at a low solar angle, near sunrise and sunset, the sun's rays would be spread over a fairly large area. To kind of demonstrate this, you can just take a flashlight and point it on a table. On the left-hand side in the figure, kind of figure A, if you have a flashlight and you are pointing it directly down above a surface, almost at a 90-degree angle, the beam from the from the flashlight would be focused over that circle, kind of circle A, if you will. So in this case, the flashlight's rays are fairly focused over a very small sort of circle. If you take the flashlight and start to move it down to a lower solar angle, you start to see that the rays are spread over a much larger area. You can try this. Take a flashlight and go pull it out, shine it on a table, and then go down to a very low angle, and you'll see that the light is spread over a much larger area. So it's not like, certain times of the day we're putting extra batteries in the flashlight to make the sun stronger. That's definitely not the case. The batteries are always on, and you can imagine that as the sun. It's just that the rays are focused over a much smaller area. So during low solar angle, sunrise and sunset, the rays are more oblique to the surface, and the energy is distributed over a much greater area, and so there is less energy per square meter. Okay? The amount of radiation coming in is always the same. I want to stress that. It's always the same. The sun just doesn't shut off at night. It's always there, and it's always emitting the same amount of radiation. What changes, though, depending on your location, is the obliqueness of the rays. So as the Earth rotates, we see the sun essentially appear to rise in the east and set in the west, even though it's nothing more than the Earth rotating. Okay, so I want to make that clear. Because of that rotational component, the beams are spread at different angles at different times of the day. The next factor is beam depletion. Okay, beam spreading and beam depletion kind of go hand in hand, but they are different physical properties going on here. Take a look at this first bullet point. Although the atmosphere is fairly transparent to incoming solar radiation, some of it can be absorbed and reflected. If we have a lot of clouds in the sky, it can reflect a lot of the incoming solar radiation. Depending on the gases that are in the atmosphere, some of the incoming solar radiation from the sun can actually be absorbed. Okay? The idea here is that the thicker or the more depth of the atmosphere that the sunlight must pass through, the greater the beam is weakened. So if you can imagine sort of a very large body of water, if you've ever been scuba diving before, you know, the first 10 to 15 feet are fine, and then eventually if you go deep enough, it starts to get very dark in the oceans because the solar rays shining into the water are becoming absorbed and reflected. It's kind of the same thing that's going on in the atmosphere. The more atmosphere that the sunlight must pass through, the more beam depletion you will receive. So at very low solar angles, such as in the morning or in the evening, the sunlight must pass through a lot more of the atmosphere in terms of depth. And I'll show you an image of that in just a second. Because it must pass through a larger depth, it looks weaker because it is more diffuse. This is the reason that in the morning and in the evening you will appear, the sunrises and sunsets will appear to be an orange or a red color, because the light is being passed through a much larger portion of the spectrum and is actually being bent a little bit. So we'll talk about that during radiation. But here's an image that kind of helps you see this. If you're sitting out here in a lawn chair and you're looking to get a tan, when the sun is directly overhead, it's only passing through a distance of the atmosphere of about 12 kilometers. So you can kind of see there's that kind of represents 12-kilometer depth of the atmosphere, and it's coming straight in and it's coming straight to you. So this would be a solar angle directly overhead, something like 90 degrees, and the light must pass through that depth of the atmosphere. So that depth being, again, about 12 kilometers or so. However, in the morning or in the evening, look at how much depth or thickness of the atmosphere that the light must pass through. So now compare this black arrow in figure A to the black arrow in figure B, and you can see that it's almost twice the distance of atmosphere that the light must pass through before it gets to you. Because it's passing through so much more atmosphere, the beam becomes depleted, and the amount of radiation that actually gets to the surface of the Earth is much less. So this beam spreading and beam depletion kind of work together hand in hand to dictate, if you will, how much radiation is received at the surface of the Earth. Okay, the last component of this has nothing more to do than the 23.5 degree tilt of the Earth, and because of that tilt, and given different times of the year, you will have either longer days in the northern hemisphere or longer days in the southern hemisphere. So keep in mind that a day is always 24 hours, right? A day never changes. 24 hours is always one day. But daylight length, or daylight hours, so the amount of hours that the sun is actually up, does change throughout the course of the year. Okay. You'll recall here in Chicago, our longest days are in the summertime, June, July, and August. Our shortest days are in the wintertime, December, January, and February. So the longer the sun is up, the more energy the Earth receives. I don't think that's pretty much a no-brainer, right? Our warmer temperatures are in the summertime, partly because the sun is up for a longer period of time, and when the sun's up, we can receive more energy. So it's really not surprising, probably to any of you, that our warmest days are in our northern hemisphere summer when we have longest daylight length. Why do these daylight hours change? It has to do with the idea of the circle of illumination. The circle of illumination is a dividing line between night and day. And because of this axial tilt, you'll see that if you were to look at a map of the circle of illumination, you can go, I encourage you to go visit www.time.gov, which is the military clock. The military clock also has a circle of illumination. It shows you basically where is night and where it's day. So you can see where sunrise is happening, where sunset is happening. In this image over to the right, you can see it'd be light over here on the left, it'd be dark over here on the right, and the circle of illumination is basically all where it's light out. That is, again, the dividing line between night and day. The circle of illumination will actually change sizes and shapes throughout the course of the year as the axial tilt relative to the incoming solar radiation changes. So in the northern hemisphere, summertime, you'll see the circle of illumination is much greater, much larger over the northern hemisphere, which corresponds with our longest daylight lengths. All right, let's break it up a little bit here. Let's have some fun. I like to do this when I'm in lecture 2. We normally take a break about halfway through our lectures, so I'd like to just throw this out here. I like to look at maps, and I like geography a lot. And there was a cool, you might have actually even seen this map before, generic names for soft drinks by county across the United States. And it's always neat to talk about humans and geography, and especially spatial patterns. And I think one of the really cool ones to start with here is the generic name for a soft drink by county. It's really interesting. Take a look down here, like towards St. Louis. You can see that nearly 80 to 100% of the people in St. Louis actually say soda, whereas you kind of creep. And actually, it's funny because I grew up down here in central Illinois, and soda's kind of creeping up the Illinois Valley area, and so you can see some of these smaller counties in here are starting to creep up higher percentages of soda. For the most part, northern and northeastern Illinois is pretty locked into saying pop, as is a large portion of the Midwest. But it's kind of cool here. You get into that Sun Belt region, into sort of the Confederate States, and it rapidly changes from pop to Coke. And I did live in Athens, Georgia for a long time, and it was interesting. If you wanted a Pepsi, a soda, or a Sprite, or whatever it was, you just always said Coke. It was kind of funny. Look at the Northeast. Almost a lot of the Northeast is soda until you get to about central Pennsylvania, and then it switches over to pop. Milwaukee is a really cool regional area that is very highly soda, where Indianapolis is very highly Coke. Then you see some very eclectic regions where you have a lot of people traveling from different portions of the country to live. So a lot of either immigration or a lot of transfer from what would be home to these areas. So take a look at the Beltway, the D.C. area, North Carolina, South Carolina. Very low percentages of everything, and a lot of others. Very eclectic areas of the country. Oklahoma City, very strongly Coke. Atlanta, very strongly Coke, where the Coke World headquarters is located. See a lot of eclectic in Alaska as well. Hawaii has almost 100% soda. I visited Maui before, and almost everybody there says soda. It's very interesting. So kind of some cool regional trends here. A lot of these places out here just don't have enough population, no data, or they're on Native American reservations, and then you can't take sort of a poll there. But you can see it's almost the difference between democratic states and sort of conservative states. It's really interesting. You'll see a lot of these kind of maps as we go on through class, and I like to share them just to show you what's going on. It's pretty cool. Okay, so for the first part of lecture, let's just do a quick review here. This is stuff that should be in your little notebook or your workbook that you're keeping to help you study for the exams as we go forward here. But just a quick review: how does the axial tilt cause seasons? Because the Earth is tilted on its axis at 23.5 degrees north, that will affect the angle at which the sunlight strikes the Earth. And that angle at which the sunlight strikes the Earth is beam spreading. Okay? The amount of the atmosphere that the sunlight must pass through is beam depletion. So remember, amount of the atmosphere, if a ray of light is trying to travel through the atmosphere and is being depleted, that would be beam depletion. The axial tilt also accounts for the amount of daylight hours. So depending on your latitude at any given time of the year, you will have 24-hour daylight lengths. And that's the interesting thing about Alaska. If you think about Alaska, in late June and early July, places near the Arctic Circle are experiencing 24 hours of daylight, yet it doesn't ever really get that hot. So even though they're experiencing 24 hours of sunlight, the sun is always at a very low solar angle, maybe 10 to 15 degrees off the horizon, and that energy is being spread over a very large area. So even though they have 24-hour days in those areas, it doesn't really ever get that warm because of this idea of beam spreading and beam depletion. Okay? So all three of these together impact the amount of energy the Earth receives at any given time of the year. All right, here's a new definition for you. This is very important for the first test. Understanding the definition of solar declination and what solar declination actually kind of means. So because of the Earth's axial tilt, any given time of the year, the sun will be directly overhead at different latitudes. Okay? So when I say directly overhead, I'm talking about a 90-degree solar angle at local noon. So over here, over the course of the year, the direct overhead solar radiation migrates between the Tropic of Cancer and the Tropic of Capricorn. The Tropic of Cancer is 23.5 degrees north. The Tropic of Capricorn is 23.5 degrees south. 23.5 degrees should not surprise you. That is the axial tilt of the Earth. So because of that tilt, you'll always see kind of this solar declination bounce back and forth from 23.5 degrees north to 23.5 degrees south. Now, during different times of the year, you can see this image here over on the left shows you at relative times of the year where solar declination is occurring. So let's just take a step back for a second. Let's define solar declination. Solar declination is defined as the second bullet point, the latitude with the direct overhead radiation. Okay? Latitude with direct overhead radiation. So solar declination is not a time of the year. Several students confuse this. They want to say solar declination is February 23rd. No, wrong. Solar declination is the latitude, the current latitude, with the direct overhead radiation. So, for instance, on March 21st, where is solar declination? Solar declination on March 21st would be directly overhead of the equator. Okay. Solar declination on June 21st would be 23.5 degrees north, the Tropic of Cancer. Solar declination on October 20th would be 10 degrees south. So you can kind of see here, every latitude experiences two solar declinations throughout the year. Latitudes at least in between 23.5 north and south, except for June 21st and December 22nd, which only get solar declination one day out of the year. And again, June 21st, you'll see here in a second, is the longest day in the northern hemisphere, and December 21st is the longest daylight length in the southern hemisphere. So, solar declination is just talking about the location or the latitude with direct overhead radiation. So, very interesting here. Okay, a lot of people think in Chicago or even in Florida, right? The sun's definitely got to be directly overhead at noon. That is wrong. In fact, even in Miami, at about 30 degrees north, the sun never gets directly overhead at that 90-degree solar angle. The 90-degree solar angle is only going to be achieved somewhere between 23.5 south and 23.5 north. True solar declination can only happen in those latitude bands, not anywhere else. Okay? So if there's a question on the exam that says, when does solar declination occur in Chicago? It's a trick question. There is no solar declination in Chicago. Solar declination can only happen somewhere between the Tropic of Cancer and the Tropic of Capricorn. The cool thing about solar declination is that we can use it to time the different seasons. All right? Take a look at this chart over here on the left. March, April, May, the Northern Hemisphere spring. June, July, and August, the Northern Hemisphere summer. September, October, November, the Northern Hemisphere fall. December, January, February, the Northern Hemisphere winter. And you can use these solar declination points and times throughout the year to help you time the four seasons in Chicago. Now, these seasons are driven by the incoming energy from the sun. Okay, right? How much sunlight do you have? How much energy is coming in? This is a pretty easy graph to understand, but it's very important. I want to make sure we break it down line by line so you can understand what's going on here. So, on the x-axis, we start at January, and we go through the annual cycle, so January through December, like a Julian day calendar. On the y-axis, we are measuring solar energy. So incoming solar energy measured in watts per meter squared. Watt is very similar to the unit that you would use to power a light bulb in your home. So all it's looking at here is energy per unit of area, and that is known as radiation. A watt per meter squared is radiation. So how much radiation is coming in at the equator during the course of the year? And I might ask you a question like, what is the range of the incoming radiation at the equator? And you can see the range would be somewhere from 450 to 375-ish, right? But throughout the course of the year at the equator, the radiation really doesn't ever change that much. Right? Again, it bounces from maybe 450 to 375 for a total fluctuation of not much over 150 watts per meter squared. Okay? So it doesn't really fluctuate that much at the equator. As you start to step away from the equator, take a look at what happens. The next blue dashed curve is 30 degrees north. 30 degrees north, we now fluctuate anywhere from 475 watts per meter squared down to 225 watts per meter squared. And when you're in the northern hemisphere, you can see that most of the incoming solar radiation is happening during May, June, and July. Take another step north to 70 degrees north, and look at how the curve now has really shaped almost like a bell-shaped sort of curve, where you have a lot of incoming radiation around June 21st and very little to no incoming solar radiation at 70 degrees north during the northern hemisphere winter season. Interestingly enough, the 70 degrees south curve is basically the opposite of the 70 degrees north curve, because when the northern hemisphere is experiencing its summer, the southern hemisphere is experiencing the winter due to the axial tilt. So you could basically take the 70 degrees north curve and shift it pi over 2 to the right, and the curves would basically match up over one another. So all of the southern hemisphere curves would just be opposite of the northern hemisphere curves. But what you can kind of see is as you progress from the equator to higher latitudes, the curves are kind of being bent in on the left. See how the equator kind of flat, and then 30 north it's bent down a little more, and then 70 is really bent down. As you increase away from the equator, we're going to see this. Lots of different graphs are going to kind of show this, but you'll see that the radiation cycle becomes more of a peak. It's less sort of constant and much more seasonally driven. So a nice graphical depiction of the seasonal cycle here. Let's start over on the right-hand side at the winter solstice. This is an important date to remember. The winter solstice happens on or around December 21st. During the northern hemisphere winter solstice, the northern hemisphere is actually pointed away from the sun. The southern hemisphere is pointed toward the sun. And the incoming solar radiation is greatest in the southern hemisphere. So on December 21st, the southern hemisphere is receiving their longest daylight length and their greatest amount of incoming solar radiation. If you progress to March 21st, you will come up on something known as the vernal equinox, or the spring equinox. And now the North Pole is neither tilted away or toward the sun. It's actually tilted at a right angle. So you can imagine the sun's rays coming towards the Earth. The tilt is actually at a 90-degree angle, and therefore it doesn't matter what latitude you're located at. All locations now actually experience 12-hour daylight lengths, and all places are experiencing equal amounts of incoming solar energy. That actually happens twice throughout the course of the year. Once on March 21st, the spring equinox, and once on September 22nd or 23rd, thereabouts, which is the autumnal equinox. So during the spring or vernal or fall or autumnal equinoxes, the North Pole is actually tilted at a right angle to the incoming solar radiation, and all locations experience 12-hour days and equivalent amounts of incoming solar energy. Go over to June 21st or 22nd, thereabouts. That is the Northern Hemisphere summer solstice. These are the longest daylight lengths in the Northern Hemisphere. This would be basically when places like Alaska and Northern Canada are having 18, 20, maybe even 23-hour days. So lots of incoming solar energy, but remember the idea of the beam spreading and beam depletion. On June 21st, the amount of incoming solar energy in the Northern Hemisphere is the greatest. We are tilted toward the sun, and we are receiving the most amount of energy that we possibly can in the Northern Hemisphere. So to make this just a little bit easier, this is June 21st. The first question that I would ask you about a graphic like this is, where is solar declination? Okay, so take a look for a second at this graph. See if you can figure out where solar declination is located. Hopefully you were able to answer that as the Tropic of Cancer. 23.5 degrees north is the latitude with direct overhead radiation. How do I know it's directly overhead? It's 90 degrees. So solar declination at this case remember the definition of solar declination is latitude. So on June 21st, solar declination is the Tropic of Cancer, 23.5 degrees north. You can see that the North Pole is tilted towards the sun's rays. We have 24-hour daylight lengths at the North Pole on June 21st. Here in Chicago, we're probably experiencing about a 14-hour day. If you go up to the Canada-US border, you have about a 15-hour, 26-minute day. And as you progress further and further into the southern hemisphere, you'll see the daylight lengths get shorter and shorter and shorter, all the way till the Arctic Circle, where you're actually receiving no sunlight for the entire 24-hour rotation of the Earth. So throughout the entire day, you actually experience no sunlight. You can imagine it can get very cold if you're receiving no sunlight. 12-hour day during a solstice is actually happening at the equator, and you can see that even then the solar angles are still very high. So even on June 21st, even though we are having very long daylight lengths in the northern hemisphere, you can see that up in these portions you're still having fairly low solar angles. So despite the fact that you get 24 hours of sunlight in the North Pole on June 21st, it's coming in at a 23.5 degree angle, so you're getting a lot of beam spreading and beam depletion. That would be an excellent test question to pose you. Even though there are 24 hours of daylight at the North Pole, why isn't it warmer there? Well, the bottom picture is actually Fairbanks, Alaska at high noon, so 12 noon, on June 21st. That is basically the highest in the sky the sun ever gets in Fairbanks, Alaska. Okay? So all day long you have sunlight, but all day long it's at that angle. So it's like it's sunrise or sunset all day long, and you can imagine that that beam is being spread over a very large area, and so the radiation, which is the energy coming in divided by the area, is much less. So you have a lot of beam spreading and beam depletion going on at the north and south poles during their respective summer times. In the winter time, or at least in the northern hemisphere winter, December 21st, we are tilted away from the sun, and now our days are fairly short. You can see our shortest day of the year in the northern hemisphere happens on or about December 21st, when our daylight length is just over 8 hours. Okay. Get down in the southern hemisphere, and you can see they're having their 24-hour days at the southern hemisphere again. The North Pole now is getting very, very cold. It's receiving no radiation at all. Into Canada, you might have a 3 or 4 hour day, but even then the sun is coming in at a very low angle, and there's a lot of beam spreading and beam depletion. The equinoxes are the times of the year when there is axial tilt, but the axial tilt is coming out of the page or out of the slide or into the page. So it's at an orthogonal or 90-degree angle to the incoming solar rays, which in this case are shining from right to left in the image. So the sun is being illuminated from right to left, but the tilt of the Earth's axis is actually out of the page or into the page, depending if we're talking about March or September. So, because the Earth's tilt is orthogonal to the incoming solar energy rays, it seems, no matter what latitude that you're at, to get equivalent amounts of daylight length. So you can see on March 21st and September 21st, it doesn't matter if you're at the North Pole, Chicago, Miami, Central America, Argentina, Brazil, Chile, you're always going to have 12 hours of daylight length. Now, just because you have equivalent amounts of daylight length does not mean you're going to have equivalent amounts of incoming solar energy. Look at this over on the right-hand side. Even though we're having 12-hour days everywhere, at the North Pole we're having a 12-hour day, but the angle that it's coming in at is about 23.5 degrees north, okay, or 23.5 degrees solar angle. In Chicago, on March and September 21st, the sun is only getting about 45 degrees above the horizon. Solar declination during the equinoxes is what? Okay, right? Take a look at this image. What is the solar declination during the equinoxes? The answer to that is the equator. So the sun is directly overhead at the equator 2 times out of the year, March 21st and September 21st during the equinoxes. The equinoxes were defined using equinox, which is a Latin term for equal night. Okay, equal night, equal day. To finish off this lecture, I'd like to talk a little bit about temperature cycles in relationship to radiation. And I like to pose the question in class, from your own experience, are spring and fall equally as warm? And most students, with a resounding no, always say fall is typically much warmer than spring. Okay, so if you're comparing fall temperatures in August, September to temperatures in March and April, you would typically say that fall is warmer, and you would be correct. Fall is typically warmer than spring, but it might not be for the reason that you think. It's actually because of this lag effect that's going on in the annual cycle of temperature. Okay, so for just a second, I want you to focus on the graph on the bottom. We have the annual cycle from left to right, so Jan to Dec, so January, February, March, April, May. And we just got done saying that in terms of the amount of incoming solar radiation in the northern hemisphere, that peaks on June 21st. So the longest daylight length, the highest solar angles, the least amount of beam spreading and beam depletion are occurring in the northern hemisphere on June 21st. That is noted by this kind of first curve right here, okay? So-called insolation curve. All right, so the insolation curve hits a maximum at June 21st. However, the curve above it is showing you the average temperature for that same location. And you would see that the temperature maximum does not coincide with the incoming solar radiation maximum. So even though temperatures peak, radiation peaks on June 21st, our warmest month out of the year is typically July or August. The warmest period in Chicago is typically the last 2 weeks in July and the first 2 weeks in August, which do not coincide with the maximum amount of incoming solar radiation. Okay? And this is kind of why this works. Imagine the insolation curve on this graph as the amount you're making in a checking account deposit. Okay? The temperature curve on this particular graph is your checking account balance. So we have a curve for deposit amount, and we have a curve for balance amount. Okay. So as we go throughout the course of the year, imagine yourself with a job and you're making more and more money, and your checks throughout the course of the year become more and more and more and more and more until June 21st, when you make a deposit into your checking account balance that is the greatest deposit or largest deposit that you're going to make all year. So essentially on June 21st, you get a check that's the largest check of the year. Okay? Your deposit amount has hit a maximum. After June 21st, we are still making a net deposit into the checking account. It's just that the amount we're depositing is not as high as it was on June 21st. Okay? Because we are still making a net deposit, the average temperature will continue to increase. As soon as we hit this surplus and deficit equality, where we are now pulling out the same amount of money that we're putting in to our checking account, that will be our net max balance account. Okay? That happens again right around August 1st. So our maximum temperatures will occur right around August 1st, when this surplus and deficit are basically equal. So again, the money is still coming. We're still putting money into the bank. It's just not as much as we were putting on June 21st. As soon as we start to withdraw more than we put in, then our temperatures are going to start to fall. But right at that balance point, that's where your temperatures are going to be maximum. So this idea is called the lag effect. Second bullet point, even though we experience the most amount of incoming solar radiation on June 21st, our temperatures do not peak until about a month and a half later, because we're still putting money into the bank. The Earth is still having a net surplus in terrestrial energy. Okay? So, in a nutshell there, it takes some time for the Earth to warm up and cool down, and that is shown in this idea of the lag effect. You also see the lag effect in day-to-day sort of radiation. You can imagine on the course of a day, when is the sun the highest in the sky? The sun is the highest in the sky during local noon, yet the warmest temperatures come around 3 or 4 p.m. It's for the same reason. We have this lag effect. We're putting the most amount of money into the bank at noon, but by 3 or 4 p.m. we're still putting money into the bank. It's just not as much as we were putting in noon. As soon as we hit that deficit and the surplus, as soon as they meet that net zero, and now we start to withdraw more money out of the bank account, that's when the temperatures essentially begin to fall. So we see this on a daily cycle, we see this on an annual cycle, and we're also going to see this on a decadal cycle as well with the oceans. All right, my last pitch for today is just to be geographically aware. I know this slide is probably funny to some of you at home, but this is the result of a lack of geographic education in our country. And you can see that this student who actually was a citizen of the United States, Lord help us all, labeling the continents and the oceans, and it's pretty much a cry for help in my opinion to be geographically aware. A lot of the weather briefings and lectures that I'm going to do throughout this course utilize United States geography and also geography around the world. So if you hear a spot that I mentioned that you're not sure of, take a look at Google Maps, take a look at an atlas or a globe, and figure out where that location is at. We need to be a little bit more geographically aware in this country than what I'm seeing with some of the students that are coming into my Introduction to Meteorology classes.